so coming to today's talk, I'm going to mainly speak about soft matter optics. I'm calling it as a Cabinet of Curiosities. The main reason being that there is so much of stuff to offer as a platform for optics via soft matter physics and soft matter material science per se. And this talk actually aims to give you an overview of how soft matter has been adapted in optics, and what can soft matter offer in optical applications, especially in photonics at micro and nano scale. And probably we will also touch upon some areas where the fact that utility of optics actually helps you to understand soft matter in much better way. So it goes in both the ways, and that's an important connection to be made. So the general definition and the category of soft matter, for example, if you look at Wikipedia, for example, soft matter or soft condensed matter is a subfield of condensed matter comprising a variety of physical systems that are deformed or structurally altered by thermal or mechanical stresses of the magnitude of thermal fluctuations. So the last point of thermal fluctuation is important because a lot of the perturbations what we have in soft matter physics generally happens to be at the room temperatures. And this has a very interesting effect on how you can manipulate the system as a function of different physical parameters, say like temperature, pressure, or external fields like electric, magnetic, or electromagnetic fields. So if you go further, the kind of soft matter which you actually come across is of very large variety. In fact, I call it as elements of cabinet because there is so much of stuff to offer from this whole kind of list. For example, liquids, colloids, polymers, foams, gels, granular matter, liquid crystals, milk that we actually consume every day, even a pillow, the flesh of our skin, and a number of biological materials. All of them actually constitute soft matter in one way or the other. And you'll see as we progress, we'll see some of the very interesting aspects of these soft matter and how they can be adapted in optical applications. So no soft matter talk is complete without mentioning the name of Perry de Jeans. Perry de Jeans went on to win the Nobel Prize in 1991 for his groundbreaking contributions towards soft matter physics. In fact, in his Nobel lecture, he makes some very interesting comments. I think I thought I'll just mention that. So he starts his talk by asking, what do we mean by soft matter? And he makes actually a kind of a nice pun against the Americans, saying that they prefer to call it as complex fluids. But in a way, the definition actually is right, because for two reasons. The complex fluids, because one is it brings in complexity. The second thing, it brings in the flexibility. Now, when I talk about flexibility and complexity, these two physical implications have very deep consequences in how soft matter interacts with external perturbation. The complexity part comes from the fact that there is a very nice evolution of systems. For example, in physics, or for that matter, even chemistry, a lot of things are evolved from atoms to molecules to, let's say, crystals or solids or liquids. And the systems actually evolve right from atomic scale all the way to, let's say, organism level complexity. That complexity is what really brings very interesting physics, chemistry, and biology to be very frank. Flexibility also comes from the fact that you can now have these complex objects which actually can interact with each other and lead to some very interesting physical and chemical properties. For example, rubber is what Perry de Jeans mentions here. But also there is a lot of other biological material. For example, surface of a cell, which actually has some very interesting physical and chemical characteristics, which are very unique and not present if you take individual entities of the cell, or for that matter, any kind of object. Moving on, coming to this particular talk, what is important for us is to ask what can we learn from the interaction between soft matter and nano or mesophotonics. So this is actually, nano or mesophotonics is kind of fancy word of doing optics at micro and nanoscale. But there are also implications of utilizing optical properties for some functional devices. So there are very interesting prospects of interfacing the soft matter and the nano mesophotonics. For example, one actually can really understand how soft matter structure, function, assembly, etc. can be studied by utilizing tools in nano and mesophotonics. So I have deliberately have this arrow two-sided, because you can not only actually utilize optical effects to understand soft matter, but you also can utilize soft matter to manipulate how light propagates, localizes, or directs on various different platforms. In this sense, in my own group, we have been interested in specific questions such as how to efficiently propagate, localize, direct, and couple light with soft matter at micro and nanoscale, and how to harness optical and opto-thermal fields to study structural assemblies and also the dynamics of soft matter. These are actually very broad questions, as I've mentioned, but the implication of addressing these questions can lead to some very interesting fundamental issues and also very interesting applications. So my job is now to just highlight these prospects during the next course of few tens of minutes. So I have divided the talk mainly into three parts. First, I'm going to actually focus on one of the very important subcategories of soft matter, which is colloids. And then I'm going to give you a very quick peek into two very interesting kind of implications of soft matter optics. One is the liquid crystal photonics, and the other one is structural colors, not only just in Beetles. Maybe I'm going to touch a little bit upon biological world and how color actually is established in biological world. Finally, I'm going to conclude with some comments and discussions, and of course, I'll follow that up with questions which you have. First and foremost, what are colloids? Colloids essentially are a stable system of two phases, one of which is dispersed in the other, and they can be actually particles, droplets. And if you observe, the definition actually is deliberately broad, because the two phases which I am talking about need not be only liquid and liquid. For example, one can have a solid particle in a liquid, one can have, let's say, a solid particle in a gas, or it can be a gas phase in a solid surface. And this can be of any different geometry. You need not only have only spherical shaped particles. So the definition of colloids per se is actually quite broad. It has huge implications, not only in terms of the curiosities, but a lot of applications what we actually look in industries, including paints, for example, food industry, or various different applications, including cosmetic industries, actually utilize colloids. They also have huge implication in medicine, biomedicine, drug delivery, etc., etc. But for now, we're going to mainly focus on some physical aspects of colloids. One question one has to ask, what is that which makes colloids so interesting? The colloids generally, the sizes what we are interested in is roughly from few nanometers all the way to few tens of microns. So the range of sizes actually is quite large. Given that the sizes are very small, one of the important implications is that there is a very large surface to volume ratio. This surface to volume ratio, if it is very high, it means that the surface plays a very critical role in the interaction. And if you subject such a surface to external stimuli, then most of the interaction or reaction happens at the interface, or rather in this particular case at the surface of the colloid. Therefore, by subjecting a colloid to an external environment, you actually can trigger or tailor the physical, chemical, and various different properties of the colloids in a very elegant way. Now, in this talk, I'm going to focus on two aspects of soft matter optics related to colloids. I'm going to talk about something called as opto-thermal assembly of colloids, and I'll also talk a little bit about self-assembled colloidal antennas. These are examples from my own work, but I'm going to also talk a little bit more about the general aspects of colloids in how they have been utilized to address some very emerging and interesting questions in science. So the first aspect where the colloids have been extensively used is in a broad topic called as active matter. So active matter is one of the very happening fields at the interface of statistical physics, soft matter physics, and colloidal chemistry, and various different branches of material science. So the definition of active matter essentially is that they consume energy, and that consumed energy actually can propel these objects in a very interesting way. They can be potentially used as robots in a fluid environment, and they actually can be utilized for various different applications. And the amazing aspect of active matter is the scaling principle, because for example, a group of flock of birds is considered as an active matter. Molecular motors are active matters. If you vibrate grains in a container, they actually constitute some kind of an active matter. So the active matter per se actually has huge kind of ambit to it. And there are various interesting questions which have evolved in recent times. In fact, nature actually has a collection, which is a kind constantly updated collection of articles, including review articles. If somebody is interested, I would strongly suggest you have a look at it. There's also some wonderful review articles, which I strongly recommend for students especially, is the addressing the aspect of hydrodynamics of soft active matter, which is actually a very interesting area by itself. And the other one is active particles in complex and crowded environments. So you can see that very important questions which cut across boundaries of physics, chemistry are being addressed in this particular area. And there is actually a very huge implication for contribution from various different backgrounds, including physics, chemistry, biology, and engineering. So, and including, of course, numerical modeling. And there's also very interesting implications from mathematics of these kind of structures, because there is a pattern recognition problem and various different questions. For this talk, we'll ask colloids, can we use it as an active optical matter? So the idea is to actually utilize an external optical field, let's say a laser beam, and ask how does this colloidal assembly interact with such a external optical field? What are the interesting implications, etc., etc. Now, most of us are aware of something called as optical traps, where you essentially have a laser beam tightly focused to a very tiny volume. And if you have a colloidal solution which is hovering around that particular tiny volume, the particles of interest, depending upon the dielectric constant and the local environment, can be potentially trapped at a single location as a function of both space and time. Now, taking this idea further, one can also create optical traps in slightly broader sense. For example, in one of the work what we have done, we have looked at something called as plasmofluidic assembly of colloidal nanoparticles. In this case, what I'm speaking about is essentially to do with the metallic nanoparticles. So the idea is the following: we actually have a glass cover slip which is coated with gold. On top of this, there will be, let's say, a colloidal fluid. And this fluid actually contains metal nanoparticles. In this case, let's say gold nanoparticles or core shell kind of particles. Now we introduce a laser beam, in this case a 532 nanometer laser beam, and you illuminate this object, which is the metal. The metal absorbs light, and that absorption actually leads to heat, and that heat actually creates a gradient of temperature, and the gradient in temperature creates a convection field, and this field actually sets the fluid in motion, and as a function of time you'll start seeing assembly of these colloidal particles at the location of interest. Now what is interesting is that you're essentially utilizing the optical field, converting that into a thermal field, and this thermal field actually sets a mechanical field, and that mechanical field further leads to some very interesting assembly processes. So we are interested in assembling colloidal particles using such kind of an optical field. So let me give you some interesting overview in terms of the videos. In this case, for example, we have silver nanoparticles on a silver film, and we do the similar experiment what I just showed. For example, if you illuminate the film, you'll start seeing aggregates of particles. What you are seeing in this video is essentially aggregates of nanoparticles, which are forming a super aggregate. So you can see that there is a kind of a elliptical shape. This comes because if you take a Gaussian beam, which is a Gaussian beam, the laser beams generally are Gaussian in function. And if you take a conic section out of a Gaussian beam, then you get an ellipse. So because you project it onto the interface, you find some very interesting assembly of colloids in this elliptical fashion. Now, what is interesting about this is that you can manipulate this assembly as a function of space and time. So, for example, you actually can switch off the optical field. You can reversibly assemble the metal nanoparticles in liquid. For example, you switch off the field, you switch it on, the aggregate comes back. And remember, all these things are happening at a metal fluid interface. So everything is actually dynamic in nature. The field is off again, and you can bring on the field again, and you can switch back and forth as a function of time. Furthermore, you actually can manipulate this aggregate in a very interesting way. See, for example, you can take a right angle turn by introducing the laser beam and moving the laser beam across this particular interface. And what you've done is, without structuring the metal film, you've been able to actually manipulate the colloidal aggregate in a 90-degree fashion. And this actually is a very interesting concept, because you have not created any microfluidic channels or anything. All you are doing is just bringing the particles, exciting them at one location, and then moving the laser beam. And wherever you're moving the laser beam, the particles actually tend to move along that particular direction. This gives you actually one more degree of freedom of manipulating the colloidal aggregates as a function of space and time. Now, there are very interesting prospects of such assemblies. It's not just you aggregate the particles, you actually can introduce molecules into these aggregates and ask whether you actually can probe single molecule processes in such aggregates. So for example, we have been utilizing Raman scattering as a tool for a very long time. So if you introduce molecules of, let's say, which are fluorescent in nature, in this case, nile-blue molecules or a rhodopsin 6G molecule, and if you look at the Raman spectra coming from the aggregate as a function of time, you will see that there's a very nice fluctuation in the Raman signature. You will also observe that there is a finite probability of detecting one particular molecule in nile-blue or the other molecule, which is the rhodopsin 6G, and there can be probability of also detecting both the molecules in this particular aggregate. By looking at the statistics and also performing some detailed mathematical analysis, one actually can prove that what we are observing actually happens to be in a single molecule regime, which means that the optical scattering which is coming from the aggregate essentially is driven by the single molecule processes, and this has some very interesting implications. So I will not go to details, but if somebody is interested, one actually can look up this paper. There's a lot of implications of aggregates and how single molecules behave in such kind of aggregates. And there are many different prospects of also studying photothermal effects on single molecules using such approaches. So if you have any questions, I'd be happy to answer later on this. Moving further, one actually can introduce more than one laser beam onto this interface. For example, in this case, we have introduced 3 different laser beams, and let's see what happens if you actually have such kind of an aggregate. Now, as a function of time, you'll see that the aggregates actually form at the location where the laser beam is there. Now, if you observe very carefully, you will also see some chains which are forming between the aggregates. Now, what one is observing is essentially a network formation. So these locations actually can act like a node, and this particular location essentially is acting like another node, but there's also now a network formed between these through excitation. Remember that there is no laser beam at these locations. What is really propagating is some kind of a field which is generated because of the excitation. So it is essentially a kind of an opto-thermal field which creates such kind of aggregation. Now, this can be studied in slightly greater detail. You can actually look at the dynamic equilibrium in such kind of structures by performing something called as particle cluster tracking measurements. So, for example, you can actually have these 3 locations, and very interestingly, the aggregate which forms at a particular location is exactly at the orthocenter of a triangle, of an isosceles triangle. So this is a very interesting geometrical kind of structure, which is kind of formed because of an emergence of this kind of nodes, and also some kind of an aggregate which gives rise to some very interesting implications in this particular case. So one can study some very important problems such as networks, and also some kind of interaction between source and drain, and kind of formations in terms of patterns in such problems. So there are very interesting implications of fundamental questions in this area. Going further, we can also look at opto-thermal assembly of dielectric colloids. In previous case, what I was talking about was mainly the colloids which were in metallic nanoparticles. You can now take, let's say, silica particles and ask what happens if you do similar experiment where you have now a triangular single crystalline gold structure. You eliminate that particular gold structure with the laser beam and ask what happens to the colloids in that particular environment. Now, one of the interesting things is that you observe a 2-dimensional crystal formation of colloids. What you're seeing here is actually roughly 3 micron colloids, which are kind of assembling as a 2-dimensional crystal around this illuminated gold particle. And this gold microplate essentially is a single crystalline in nature. And when you illuminate, this actually creates heat. And again, the fluid actually is now set into motion. But as a function of time and space, there is a very nice 2-dimensional crystal which is formed. One can analyze the various different parameters of this crystal, but I'm going to skip that and guide you towards this particular publication. This is a recent one, and if you're interested, I would urge you to have a look at it. Moving further, can we use colloids to prepare an optical antenna? Now, optical antenna is a very interesting prospect. You essentially actually have a transmitter and you have far field radiation. What does an antenna do is to take this transmitter, which is a tiny scale, and ensures that there is an efficient projection of this light which is coming from the transmitter to the far field. The time reversal process can also be very interesting. One can actually have light from the far field projected onto a receiver mediated through an antenna. Now remember, this transmitter or receiver can be a molecule, an atom, or any kind of emitter. It can be even a quantum dot, for example. This is a very interesting area of research because the physics is not just merely a scaling problem, but it also has to do with the change in size and shape of the antenna structure, and also how metals behave, or for example, electrons behave once you shrink structures to a smaller and smaller extent. So the problem actually is very interesting, and it's one of the very happening areas of research. And the question we ask is, what happens if you have an antenna which is made of soft material, for example, a colloidal structure? So one of the things which we are interested in is something called as whispering gallery modes. So this is something which is very well known in optics community. If you look at a sphere and you illuminate the sphere at a very particular angle, you tend to actually get total neutral reflection. So you end up actually having something called as whispering gallery modes. These whispering gallery modes actually are the modes of a sphere which actually are confined to a particular plane, or it can be also confined to the whole of the sphere, depending upon the projection of the numbers. In this particular case, the angular and the quantum numbers, the radial, angular, and azimuthal quantum numbers. And it also depends on the polarization of the light which is incident. Now, microspheres, the colloids actually can do this. Okay, for example, an SiO2 particle actually can give rise to whispering gallery modes. And these resonances of the modes actually are very, very sharp. Now, wherever you have a very sharp resonance, it means that the quality factor of that particular resonance is very high, which also tells you that these spheres actually can be utilized for very sharp resonances, and hence one can utilize it as a optical sensor. And in certain cases, if you do the experiment properly, you can actually also utilize it as a laser. So which means that the implication actually is very, very huge. What we have shown in recent time is to actually take such a kind of a resonator made of colloidal sphere, in this case, for example, a microsphere, and couple it to a silver nanowire. And a silver nanowire is a plasmonic resonator in a sense. In this particular case, we incident laser light onto the wire, and then we project the plasmon across this particular wire. During this particular transport of the plasmon, this can actually further excite the microsphere and can lead to some very interesting properties. So shown here actually is some of the electron microscopy images and also the optical images of such coupling. We actually have a protocol of preparing such structures. We utilize self-assembled process of coupling the wires to the sphere. It's very interesting process, and it also is of very high interest among the soft matter community of the process of self-assembly of these kind of hybrid structures. One can now see that you can excite the sphere at one location and look at the light coming out of the sphere at a remote location. Because now you have been able to excite the sphere through the wire, this actually acts like a remote excitation of the sphere. And therefore, you actually can utilize it for some very interesting applications, etc. For example, one of the questions we are interested in is whether we can look at this as an antenna. So for example, we can compare the angular distribution of the fluorescent light, which is actually emanated from the sphere. If you take a single isolated sphere, the light which is coming out of the sphere is isotropic in nature. So this actually experiment tells you, or rather quantifies, that particular isotropic emission. Whereas if you now couple the sphere to the wire, you will now suddenly bias the emission in a specific angle, which means that by coupling the sphere to the wire, you've been able to actually direct the light from the colloidal sphere in a particular direction. And this has huge implications in antennas and in optical antennas and on chip scale photonic processes, etc., etc. Now, we have been using this particular strategy also to do some very interesting experiments. For example, if you look at a gold film and a nanowire, and you have molecular layer sandwiched between these two structures, you can now incident light and look at what is the light which is coming out of it. And this particular light which is coming out is essentially a convolution of the optical resonances between the film and the wire. And you actually can do this experiment, and we can observe some very interesting effects. I'm not going to go into the details, except to mention that the way molecular emission behaves in such kind of hybrid cavities is not trivial. That is, for example, the Raman scattered light is distributed across all the directions, whereas the fluorescence light actually is distributed only in one particular direction, or rather more biased in one particular direction. So there is huge implications. It's kind of a special strategy, and it works interesting for certain kind of applications. Now, I'm going to give you a very quick peek of two other applications. This is something I'm personally very interested, something we are tending to develop, but the work which I'm going to present is actually from other groups. And there's a lot of interest in liquid crystals. As you may know, liquid crystals are a great category of soft matter systems, and they have huge implications in photonics, obviously, including displays and other kind of technologies. And there's also something called a structural color in biological world, which actually has implications in, again, display and other kind of applications. But the question itself actually is of very high interest in fundamental physics and chemistry community. So Liquid crystals, I assume most of you will be aware of it, but for the sake of completeness, they are essentially a substance which flows like a liquid, but has some degree of ordering in the arrangement of its molecules. In a way, kind of a crystal. The important aspect is the liquid crystals actually have different phases. For example, one can have nematic phase, where the molecules, individual molecules, are aligned in roughly aligned in one particular direction. There's a kind of a director field which you actually can define. You can actually have cholesteric liquid crystals, which actually bring in the chirality in such kind of structures. Smectic crystals, which actually have some kind of arrangement, which is quite interesting. One can have smectic A and B phases, or a smectic C phase with a tilt with respect to the director field. Columnar fields, rectangular, herringbone, etc., etc. I should mention that in the Indian research community, especially there is a very huge implication of liquid crystals and a contribution from the liquid crystal group of Chandrasekhar at RRI, where S. Chandrasekhar, who actually was one of the pioneers in the liquid crystals, has contributed to a great extent in bringing out some new structures in liquid crystals. So I would urge you to have a look at the history of liquid crystals, and you'll come to know about it quite a bit. Now, what can you do with liquid crystals? Liquid crystals actually are excellent for performing photonic operations. For example, I would urge you to have a look at this very interesting review article where liquid crystal microphotonics is described in detail. So one of the very attractive aspects is that you actually can introduce colloids into liquid crystals. So these are all optical images, by the way. They're actually look like very fancy designs, but they're essentially an experimental image, what you actually can get in an optical microscope. So you see colloids which are now assembled in a liquid crystal in a very interesting fashion. These are so-called dipolar colloids, and you can also assemble these colloids in a very interesting wavy fashion, which gives rise to something called as quadrupolar colloids. The dipolar and quadrupolar are essentially to do with the topological defects which these crystals actually give rise to. You actually can have combination of sizes of colloids which form an array, and these arrays actually can give rise to very interesting photonic band gaps in such kind of structures, and these are all inside the liquid crystal. So you actually can look at the two-dimensional patterns and assemblies. You can also have very interesting assemblies of two different sizes of the particles, where the smaller particles actually assemble at the defects formed of the larger particles, and you can also manipulate the topological defects in the array and have some very interesting assemblies of these kind of liquid crystals. Now, what is the implication of this? The implication is that you can utilize such kind of colloids for various different applications. For example, understanding how matter behaves in an anisotropic environment. In fact, that is a very important question, because if you look at it, the problem of understanding cargo transport inside a cellular environment actually is not very different from a colloidal particle moving in a liquid crystalline environment. Now, liquid crystal is slightly more idealized situation, and a colloid is also an idealized situation. But you need model systems to study such kind of idealizations. So therefore, these systems serve very well, and they actually can also give rise to some very important implications in understanding light matter interaction and various different questions. Now, in terms of practical applications, liquid crystal droplets actually have turned out to be very interesting. So for example, shown here is a liquid crystal droplet, essentially of roughly around 3 microns in radius. And if you look at the liquid crystal droplet in a cross-polarized microscope, you will observe that it has some very interesting molecular assembly, which gives rise to this birefringent pattern. By applying an electric field, where you actually have taken this liquid crystal droplet and kind of put it into a small chamber, and you apply an electric field across this particular chamber, you can now induce a transition in terms of the phase from one particular alignment to another particular alignment. Now, not only is there a phase transitions, remember I also spoke about the whispering gallery modes. The whispering gallery modes are also available in such kind of spheres. And the important implication is that you incident light onto such kind of droplet and you change the electric field, the wavelength of the resonances actually can be tuned as a function of electric field. This is one of the remarkable properties of liquid crystals, because you actually can actively control the molecular alignment in a confined geometry, which is very hard to do. For example, if you take a silica particle or something like that. And of course, these droplets can also be utilized to obtain lasing, which means that you actually can create a tiny laser out of such kind of droplets. You can introduce such droplets in various different environments. One of the really happening fields in this particular area is something called as biological lasers, where you introduce a droplet into a biological environment and see whether the droplet actually can act like a laser, which means that you don't have to have an external laser. You actually can have an internal laser inside a biological environment. So there are very interesting implications in this area. Next, I'll switch over to one of the other fascinating concepts where biological world actually can give rise to very interesting nano-optical effects. For example, beetles, butterflies, birds, moths, there's a variety of organisms which actually can give rise to very interesting biological implications. Most of the time we know that the color is generated using pigments. But there is also another way of generating color, which is called as structural color. These colors actually are generated because the way microstructures are arranged on top of on the surface of, let's say, a biological organism. For example, you actually can create color due to interference. Most of you would be aware of that, especially when you go out and if there's a thin layer of oil and water, you'll see interference patterns, which is it's quite evident when we observe that. There's also color generation due to diffraction and scattering, etc., etc. In fact, this particular review article I strongly suggest. It's a very nicely written article, also has a very interesting historical implication. One of which is which is quite interesting. Newton was the first to suggest that such brilliant iridescent colors in birds and insects might perhaps be due to the presence of thin film structures, as he had observed the color producing properties of such thin films. Newton is known for many things, but he's also one of the pioneers in optics. Many of you probably are aware of. There's also another big person from India, C.V. Raman, who was also obsessed with optics, who was outstanding in terms of actually connecting optical processes to a natural environment. And he also has contributed to this particular area. And I would strongly suggest you have a look at this paper, and also volumes of papers which he has written, including floral colors and visual perception, which is actually volume number 6, if I'm correct, of scientific papers of C.V. Raman. In fact, in my office, I'm just seeing that particular book right in front of me. It's quite interesting in that sense. So what is interesting about this is that biological surfaces actually can give rise to very rich variety of colors. For example, generating blue is not a very trivial thing. You need to have a very strong scattering to generate blue color out of white light. You all know the color of the sky is blue because there is some kind of Rayleigh scattering phenomena. But also you can generate blue color from the structural periodicities. For example, this is a particular kind of a species of butterfly, and the butterfly actually gives rise to very interesting angle-dependent coloration because of the way the feather actually is structured. So these structures roughly are of the scale bar here is roughly around 1 centimeter, or rather scale bar is roughly around 1.8 centimeters, roughly 2 microns about. So you can see that the periodicity is actually quite high, and this is the structure which gives rise to very interesting coloration. There's another species which does not have the same density of coloration, density of the structure, and therefore the light which scatters off that particular object actually would not give rise to the blue color. Instead, it actually gives rise to some other different color. Now, this actually has huge implication. It's just not curiosity, because you can now utilize this for display technology. You can actually now look at the structures which are available in nature, in biological world, and try to actually mimic that particular structure in an artificial environment and create displays which actually are either angle sensitive or angle insensitive. In fact, angle insensitive projections are very important. For example, if you want to actually have a particular display be evident across different angles, you need to have an angle insensitivity. And that is one of the important applications of this. The other one is fantastic beetles. These beetles actually are very interesting structures, something called as jeweled beetles. And when you actually incident circular polarized light, if you have a left circularly polarized light, you actually have this brilliant green beetles. Whereas if you have a right circularly polarized light, they actually are reasonably dark. Now, you know that once you actually have circular polarization sensitivity, then there is something related to the chirality. Most of you would be aware of this. And there is a very interesting structure related reason for this, because there are some hexagonal cells in this particular beetles, which gives the selective scattering of only certain colors in a particular direction. Whereas in right circularly polarized light, because of the handedness of that particular hexagonal cell, you would not observe this. In fact, so much so that there is a very interesting connection between such kind of beetles structures and also the cholestic liquid crystals, which are a category of liquid crystals which gives chirality in the environment. So to conclude my talk, there is a lot more. What I've spoken now is just a very, very tiny bit in a very large metaphorical ocean. There are surfactants, polymers, gels, foams, binary liquids, including droplets, bubbles, whatnot. The list actually is almost kind of doesn't end. It's such a great cabinet of curiosity indeed. Now, the combination of soft matter and photonics is not just only driven by curiosity. Of course, this is actually a very important element, but also there's a huge amount of fundamental science which is yet to be kind of discovered and also invented in certain sense. And obviously, there are some major applications which have already been kind of realized. And in foreseeable future, there will be surely a lot of implication. So much so, for example, if you look at the current aspect of detecting a virus, one of the important questions people are asking is, can we optically detect, let's say, the COVID virus? And the answer is yes. We actually can utilize label-free techniques or label techniques. For example, you can utilize light scattering techniques such as interferometric scattering microscopy, which actually can give rise to some very interesting kind of projection of the optical information from a single nanoparticle. And in a virus in this particular case is roughly around 150 nanometers. So you actually can potentially utilize an optical microscope to detect that, but you need a specialized optical microscope. General ones can't detect because of the diffraction limit, but you have to overcome that barrier by using some smart techniques. And finally, let me again end with something which is related to Perry Dejean's Nobel lecture. He concludes his own lecture by citing a poem from an experimental soft matter. It's a kind of poem from experimental soft matter, which reads like this: have fun on sea and land, unhappy it is to become famous. Riches, honors, false glitters of this world, all is but so bubbles. With this, let me acknowledge my co-workers, my current PhD students who are all actually now in various different parts of India because of the lockdown, and the former postdocs and former PhD students who are also hopefully all doing fine, and former MS students. And our funding comes from various different sources, including Department of Science and Technology within India, and also some international funding agencies. And finally, thank you all for your patience and listening to my talk. Thank you. Thank you very much.